Angular momentum of a particle L vector. It is defined as the product of magnitude of linear momentum of the particle and perpendicular distance between the origin and the line of momentum. This is shown in the figure. This is y-axis, this is the x-axis, x-dash axis. Now a point P is here, moving with velocity v at any time, and its mass is m. Then its momentum will be p, that is m into v vector. And this is a radius vector of that point mass, and this angle is theta, that is the relative max angle with radius vector theta. And we draw a perpendicular on the line of velocity or momentum. uh, this is OR, the perpendicular distance. So L equals to mod of P into OR, uh, P into OR in triangle ORS. Sin theta equals to OR by OS. This implies OR equals to OS sin theta equals to R sin theta. Hence L equals to P into R sin theta or equals to R into P sin theta, or L equals to R into MV sin theta equals to R into P sin theta, equation 1, where theta is the angle between R vector and P vector. In vector form, this can be written as L vector equals to R cross P or RP sin theta n cap, where n cap is a unit vector perpendicular to the R and P vector, where n cap is a unit vector whose direction is given by right hand screw law. Thus, angular momentum vector is also defined as the cross product of position vector and linear momentum of the particle. Here L equal to Rp sin theta, we can write it as R into P sin theta, and R equals to P perpendicular. Here you see this is the P vector. There will be two components along in this line P cos theta and along this line P sin theta. This is the perpendicular component of P vector. So it is written as PR, and this is the radial component. So it is written PR P cos theta. Now we see that from the formula Rp sin theta, this can be written as R into P sin theta or R into PR sin theta, because PR equals to P sin theta. Again L equals to Rp sin theta R sin theta into P. So we can write R perpendicular into P. L vector equals to R cross P vector, Rp sin theta n cap. Mode of L vector is 0 when R equals to 0 or P equals to 0 or theta equals to 0 or 180 degree. Question: a particle of mass 4 kg is moving with velocity 2i cap plus 3j cap plus 3k cap meter per second. The position vector of particle at that instant is 2i cap minus 3j cap plus 2k cap meter. Find the angular momentum of the particle at that instant. Solution: P vector equals to mv vector 4 into this 8i cap plus 12j cap 4k cap kilogram meter per second. Now we know that L vector equals to R cross P vector. So arranging it in determinant form, I, j, k, and the first row will represent the component of R vector, that is 2, minus 3 and 2, and the last row, the third row, represent the component of P vector 2, 3 and 3. And solving this by the rules, that is when we take I cap, then this will multiply minus this multiplication, minus 3 into 3 minus 9 and minus 2 into 3 6 minus 6. Again when we take j cap, then 2 into 2 minus 2 into 3 4 minus 6. When we take k cap, then 2 into 3 minus of minus 3 into 2 k cap 6 minus of minus 6, and kg meter per second square, kg meter square per second, the unit of angular momentum. Finally, we get minus 15 I cap minus 2 j cap plus 12 k cap kilogram meter square per second. And magnitude of angular momentum will be given by this formula. Relation between angular momentum and torque of a particle. We have L vector equals to R cross P. Differentiate now. There is a formula for differentiation. If A cross B, then we can find it d by dt A cross B as dA by dt cross B plus A cross dV by dt. This is the formula. We will apply this formula in this here. Differentiates with respect to time. dL by dt equals to d by dt R cross P. So from this formula we can get dr by dt cross P plus R cross dP by dt. Now dr by dt is equal to V. So V cross mv vector, P, because P vector is momentum, so m into V vector, and R cross dP by dt equals to R cross dP by dt, because V cross mv vector mode of V mode of mv sin 0 degree, because same vector is cross producted, so its value will be 0 vector. So only we are left with this term R cross dP by dt. This implies dl by dt equals to R cross f, because dP by dt is equal to f vector, so R cross f, and R cross f is equals to the tau vector. So rate of change of momentum is given by tau vector. So we can say that rate of change of momentum is equal to the torque of the body. Torque, or dl by dt equals to tau. Thus, time rate of change of the angular momentum of the particle is equal to the torque acting on it. We have linear dp by dt equals to f, that is time rate of change of linear momentum is equal to the force. And in rotational, dl by dt equals to tau, that is time rate of change of angular momentum is equal to the torque. Torque and angular momentum for a system of particles. The total angular momentum of a system of particles about a given point is the vector sum of individual angular momentum of all particles in the system. That is, L vector equals to L1 plus L2 plus dash 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 Ln. Sigma I equals to n Li vector, where I is the generalized term, where Li vector equals to Ri vector cross Pi vector is the angular momentum of the ith particle, a generalized ith particle. Now Ri vector position of the ith particle, and Pi vector is the linear momentum of the ith particle. Now L vector equals to sigma Li vectors equals to sigma Ri vector cross Pi vector. Equation 2. Differentiating with respect to time, we get dl by dt equals to d by dt sigma Li vector. Sigma I dli by dt equals to sigma tau I vector, which will be equal to total term tau vector. So dl by dt equals to tau vector, where tau I vector is the torque acting on the ith particle. This symbol is written as tau, where tau I vector is the torque acting on the ith particle. Now tau I vector equals to Ri vector plus Fi vector. So, and Ri cross Fi external plus Fi internal equals to Ri cross Fi external plus Ri cross Fi internal, where I vector position of the ith particle and Fi is the net force on the ith particle. Fi vector is the net force on the ith particle, Fi external is the net external force on the particle, and Fi internal is the net internal force on the particle. Now tau I vector equals to Ri vector plus Fi directly. Now, tau vector equals to sigma tau I vector equal to sigma ri cross fi external plus sigma ri cross fi internal equals to tau external plus tau internal, equation 5. Now, torque due to internal forces cancel out in pairs, and so net internal torque of the system is 0, that is tau internal equals to 0. So equation 5 becomes tau equals to tau external. Thus equation 3 becomes dl by dt equals to tau external, that is rate of change of angular momentum is equal to the net torque, net external torque acting on the particle or body. Thus, the time rate of total angular momentum of a system of particles about a point is equal to the sum of the external torque acting on the system taken about the same point. Conservation of angular momentum. We have dl by dt equals to tau external. If tau external equals to 0, then dl by dt equals to 0. And this gives L vector equals to constant. Thus, if the total external torque on a system of particle is 0, then the total angular momentum of the system is conserved, that is remains constant. If tau external is equal to 0, then L vector equals to constant. This implies Lx equals to constant, Ly equals to constant, and Lz equals to constant, where Lx, Ly and Lz are the component of angular momentum along x, y and z axis. Equation: find the torque of a force 7i cap plus 3j cap minus 5k cap about the origin. The force acts on a particle whose position vector is I cap minus j cap plus k cap. We know that tau vector equals to r cross f vector. Arranging it into determinant form and writing the value of r and f and solving like this. Finally, we will get 2i cap plus 12j cap plus 10 cap as a tau vector. Next question is, show that the angular momentum about any point of a single particle moving with constant velocity remains constant throughout the motion. So that the angular momentum about any point of a single particle moving with constant velocity remains constant throughout the motion. Here the situation is shown. Consider a particle P is moving in this direction with velocity v. At that time, the position vector, this is the origin. At that time, the position vector of particle is r vector, and after some time it reaches at this point, and at this point its position vector becomes r dash vector. Now, if we draw a perpendicular on this line, that is along the line of velocity, that is OM. OM is the perpendicular from origin on the line of velocity. So this will be r sine theta, because in triangle, in this triangle OMP, sine theta will be OM by OP. So uh, this value OM will be r sine theta. So now we know that from the definition of angular momentum, it is equal to the linear momentum multiplied by perpendicular distance between point of rotation and line of velocity. So here is linear momentum equals to mv, or L equals to, that is momentum, linear momentum equal to mv, and perpendicular distance between point of rotation and line of velocity. This is the perpendicular distance uh, from the point of rotation to the line of velocity. So mv into r sine theta. Now whatever be the position of the particle, perpendicular distance, that is OM, remains constant. So the angular momentum remains constant. So the angular moments remains constant. Next, equilibrium of rigid body. Unless stated otherwise, the force or torque means net external force and net external torque. A rigid body is said to be in mechanical equilibrium if both its linear momentum and angular momentum are not changing with time, or equivalently, the body has neither linear acceleration nor angular acceleration. This means that 1. The net force on the body is 0, that is F net equals to F1 plus F2 plus that is Fn sigma Fi equals to 0. Similarly, if net force on the body is 0, then linear momentum of the body does not change with time. This is the condition for translational equilibrium of the body. Second, the net torque on the rigid body is 0, that is tau net equals to tau 1 plus tau 2 plus tau n sigma tau I equals to 0. If net torque on a body is 0, then the total angular momentum of the body does not change with time. This is the condition for rotational equilibrium. So mechanical equilibrium represents that, here it is shown. For translational equilibrium, F net should be 0, so P will be constant. And for rotational equilibrium, tau net, that is torque, total torque should be 0, so angular momentum will be constant. And from this, sigma Fi equals to 0. This gives sigma Fi x equals to 0, sigma Fy x equals to 0, sigma Fi z equals to 0. And this gives sigma Ix equals to 0, sigma tau Ix equals to 0, sigma tau Iy equals to 0, sigma tau Iz equals to 0. For a particle, only translatory equilibrium is considered. For particle, only translatory equilibrium is considered, because particle is not a body, it is a point like. So only particle can translate, cannot rotate. So we have to consider only translatory motion for particle. Now partial equilibrium. If the body is in either translational equilibrium or in rotational equilibrium, then it is called in partial equilibrium. Here sigma f equals to 2f vector, sigma f is not equal to 0. And sigma tau equals to tau 1 plus tau 2, af into n cap minus af into n cap equals to 0. It is shown here, where n cap is the unit vector perpendicular to the plane of paper in outward direction. So A, rod AB is not in translational equilibrium because sigma f is not equal to 0. And B, rod AB is in rotational equilibrium because sigma tau equals to 0. So this is the case of partial equilibrium. Now couple. A pair of equal in magnitude and opposite forces with different lines of action is known as couple. It produces rotation without translation. Here a situation AB is a massless rod and C is the point where it is clamped. Now if we apply a force in this direction at this point and same magnitude of force in this direction, if this will be F vector, then this will be minus F vector. Now we know that tau vector is net torque on the this AB will be tau C, that is about C equals to tau 1 plus tau 2, and this equals to A into mod of F into n cap plus A into mod of minus F into n cap, which gives F into n cap plus F into n cap equals to 2F n cap, and this is called couple. So that moment of a couple does not depend on the point about which you take the moment. Here it is the AB is consider a rod, and O is the origin or reference point, and F force is acting in this direction, and same magnitude of force is acting anti-parallel to this force, that is in this direction, that is this will be minus F vector, and the position of A is R1 vector and position of B is R2 vector. The moment of the couple equals to the sum of the moment of the two forces making the couple, that is equals to R1 cross minus of F vector plus R2 cross F vector, or R2 cross F minus R1 cross F. If we take out of F vector, then R2 minus R1 cross F vector, which is equals to AB cross F vector. Thus, moment of couple is independent of origin. We see that moment of couple is independent of origin because there is no R1 and R2. Principle of moment, lever. A ideal lever is essentially a light rod pivoted at a point along its length. This point is called fulcrum. Here a rod AB is shown, which is pivoted at this point, and it is called fulcrum, and this distance is D1 load arm, which is called load arm, and this is the effort arm D2. Here F2 force is applied, and here F1 load is applied. For translational equilibrium, R minus F1 minus F2 equals to 0. If you want to put it in a translational equilibrium, that all forces on this must be equal to 0. So R minus F1 minus F2 equal to 0. This gives R equals to F1 plus F2, equation 1. Now for rotational equilibrium, net torque must be 0 about this fulcrum. So F1 into D, force into perpendicular distance. D1 is the perpendicular distance, our force is F1. The F1 into D1 minus F2 into D2. F1 into D1 plus minus of F2 into D2 equals to 0. This implies F1 D1 equals to F2 D2, or load into load arm equals to effort into effort arm. The above equation expresses the principle of moment for a lever. Now mechanical advantage MA. It is the ratio of load and effort. That is MA equals to load divided by effort, or F1 by F2 equals to d2 by d1 effort arm by load arm. If MA is greater than 1, d2 by d1 is greater than 1, or F1 by F2 is greater than 1, this implies d2 is greater than d1 and F1 is greater than F2. That is, if effort arm is greater than load arm, then load is greater than effort. That is, less effort is needed to lift the load.